A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Corn, this whole show runs on GPU compute, and we wouldn't be here without Modal.
Seriously. And that's what powers all our text-to-speech. Everything you're hearing right now.
They're an AI infrastructure platform. Developers use them to run GPU workloads in the cloud with zero infrastructure headaches.
If you're building anything with AI, check them out. Modal.com. I was looking at some benchmark data this morning, and it hit me that we are living in the era of the infinite prompt, yet companies are still spending millions on specialized training. It feels a bit counterintuitive, doesn't it?
It really does. You'd think that with context windows stretching into the millions of tokens, we're seeing models now that can ingest the entire codebase of a Fortune 500 company in one go. We'd just be shoving entire libraries into the prompt and calling it a day. Why spend 6 weeks training a model when you can just copy-paste the manual into the system message? But today's prompt from Daniel is actually forcing us to look at why that isn't happening. He wants us to dig into the staying power of fine-tuning for large language models and multimodal systems, especially as we get into 2026. Oh, and before I forget, I'm Herman Poppleberry.
And I'm Corn. You know, Herman, I feel like every time we talk about this, the goalposts move. A year ago, people said RAG retrieval. Augmented generation would kill fine-tuning. Then they said long context would kill RAG. Now we're sitting here with Google Gemini 3 Flash, which, by the way, is powering our script today, and we're still talking about weights and biases. Why are we still tinkering under the hood when the engine is already so massive?
Because a massive engine doesn't mean it knows how to drive a Formula One track. If you take a semi-truck engine and put it in a Ferrari, you have power, but you don't have the specialized performance required for the circuit. Daniel's prompt hits on 3 big pillars: domain expertise, style, and niche task optimization like Text-to-SQL. And the nuance here is that in 2026, we aren't fine-tuning to give the models facts QS anymore. We have RAG for that. We have 10 million token context windows for that. We fine-tune to change the model's behavior. It's the difference between giving a student a textbook and actually putting them through medical residency.
I like that distinction. It's not about what it knows, but how it thinks. But let's start with that first pillar, domain expertise. If I have a trillion parameter model that has read every medical journal on the internet, why do I still need to fine-tune it for a hospital system? Isn't the knowledge already in there?
It's in there, but it's buried under a mountain of internet speak. When you prompt a general model about a specific pathology, it might give you a great answer, but it's using the statistical average of how people talk about that pathology across the whole web. That includes Reddit threads, old blog posts, and general news articles. In a specialized clinical setting, you need the model to prioritize a very specific reasoning path. You need it to understand the shorthand, the specific acronyms of that hospital, which might mean something totally different in a legal or engineering context, and the way a senior consultant would weigh conflicting evidence. Fine-tuning adjusts the latent space of the model so that these professional neural pathways are the path of least resistance.
But wait, how does that work in practice? If the model already knows the acronym CAD stands for coronary artery disease, but also computer-aided design, doesn't the prompt just tell it, hey, we're in a hospital? Why isn't that enough?
Because it's about the probability of the next token. In a massive model, the attention is spread thin. If you prompt it, you're asking it to ignore 99.9% of what it knows. Fine-tuning actually reshapes the internal landscape. It's like a city where the model used to have to take a winding back road to get to the medical center district. After fine-tuning, you've built an 8-lane highway straight there. It doesn't just know the medical stuff, it defaults to it. It understands the hierarchy of importance. For example, a general model might list 5 possible diagnoses with equal weight. A fine-tuned clinical model knows that in this specific demographic, for this specific clinic, 3 of those are highly unlikely, and 1 is an emergency that needs to be mentioned first.
So it's like if you're a polyglot who speaks 20 languages, but you're currently in a room full of French architects. You could speak English or Japanese, but you've tuned your brain to only operate in the specific jargon of French architecture for the next 6 hours. It reduces the token tax, as Daniel mentioned.
Well, not exactly, but you've got the spirit of it. The token tax is a huge deal. If you're using a long context window to explain your company's entire internal logic, your 50-page compliance manual, and your 200-item style guide every single time you send a prompt, you're paying for those tokens over and over again. You're also introducing distraction. Models, even the best ones in 2026, still suffer from lost in the middle or getting distracted by irrelevant details in a massive prompt. Fine-tuning bakes that logic into the model itself. It becomes its vibe, for lack of a better word.
It's vibe. I love it when you get technical, Herman. But let's talk about the second pillar, style and brand alignment. This seems like the marketing department use case. Is this just about making the bot stop saying as an AI language model and making it sound more like a cheeky brand mascot?
It's deeper than just the catchphrases. Think about a high-end concierge service. It's not just about saying, "Hello, sir." It's about the cadence, the level of deference, the way it handles refusal. If you try to do that with just prompting, what we call in-context learning, you often get instruction drift. The model starts off great, but after 20 exchanges, it starts reverting to its base training. It forgets it's supposed to be a 1920s noir detective and starts sounding like a helpful assistant from Silicon Valley again.
I've seen that. You're halfway through a Dungeons and Dragons campaign, and the dungeon master suddenly tells you that it's important to maintain a respectful and inclusive environment, instead of telling you the orc is swinging a mace at your head. It kills the immersion.
Right, and for a business, that drift is a liability. If you're a luxury brand like Rolex or Porsche, you can't have your agent sounding generic. Fine-tuning locks that persona in. It's not a suggestion in the prompt, it's a fundamental part of the model's probability distribution. It wants to speak in that style. It's like the difference between an actor wearing a costume and an actor who has spent 6 months in character using the method. The method actor doesn't have to keep checking the script to remember how they should stand or talk.
But couldn't you argue that with 2026 models having such high reasoning capabilities, they should be able to hold a persona indefinitely? Why does the drift even happen?
It's a fundamental property of how transformers work. Every new token generated is added to the context. Eventually, the original system prompt that said, "You are a pirate," is buried under 10,000 tokens of the actual conversation. The model's attention starts focusing more on the recent conversation than the initial instructions. Fine-tuning solves this, because the pirateness isn't in the context window, it's in the weights. Even if the context window is empty, the model is still a pirate.
Now, Daniel's third point was about niche tasks, specifically Text-to-SQL. This is one that actually impacts the bottom line for a lot of tech companies. Why is a fine-tuned small model often better at writing database queries than a massive God model like GPT-5?
This is one of my favorite topics because it defies the bigger is always better logic. Writing SQL is a very rigid logical task. A general purpose model is trained to be creative, to be conversational, to be human-like. But a database doesn't care about your personality. It cares about syntax and schema. When you take a smaller model, say a 7B or 14B parameter model, and you bombard it with thousands of examples of English question, SQL query, it becomes a specialist. It learns the specific quirks of SQL syntax that a general model might hallucinate.
Can you give me a concrete example of a SQL hallucination? I thought SQL was pretty standard.
Oh, far from it. Every database dialect has its own weirdness. PostgreSQL versus MySQL versus Snowflake. A general model might try to use a t-limit clause in a dialect that uses tfetch firsty, or, more commonly, it misses the join logic for a specific, non-standard company database. If your company uses a weird naming convention where customer ID is actually stored in a table called x77userref, a general model will never guess that. But a fine-tuned model has seen that schema 5,000 times during training. It doesn't have to guess. It also learns the specific schema of your database without you having to describe every table and column in every single prompt. It's faster, it's cheaper, and because it's a specialist, it has a much lower error rate on that specific task.
It's like hiring a general contractor versus hiring a master plumber. The general contractor knows how plumbing works, but the master plumber has the muscle memory. He's seen every type of leak. He's not thinking, he's just doing.
That's a decent way to put it. And the cost element is massive. If you're running 1 million SQL queries a day, doing that on a frontier model costs a fortune. Doing it on a fine-tuned Llama 3 or Mistral running on your own hardware, that's pennies. We're talking about a 90% reduction in operational expenditure for the same, or often better, accuracy.
But Herman, if I'm a developer, how do I actually seize the difference? Is it just that the code runs, or is there a structural difference in how the fine-tuned model handles the logic?
It's both. A general model often writes fragile, SQL. It might work for a simple select statement, but when you ask for a complex window function or a recursive CTE, the general model starts to guess based on what it saw in a Stack Overflow post from 9 years ago. A fine-tuned model for Text-to-SQL has been trained on valid, executable code that matches the modern standards of the specific engine you're using. It understands the intent of the query. If you ask for sales from last quarter, the general model might just use a generic date range. The fine-tuned model knows that your company defines quarters based on a fiscal year that starts in April. That's a huge distinction in a production environment.
So it's not just about the language, it's about the institutional knowledge baked into the syntax. That seems like a massive safety feature too. You don't want a bot accidentally running a drop table command because it got confused by a prompt.
You can actually fine-tune for negative constraints. You can train the model so that the probability of it ever generating a destructive command like etdropt or tdelete is effectively zero, regardless of what the user asks for in the prompt. You're building a sandbox into the brain of the model itself.
All right, so we know why people do it. But let's get into the how. Daniel asked about the process and the investment. I think a lot of people still think fine-tuning requires a PhD and 1,000 H100s in a basement. Is that still the case in 2026?
Not at all. The barrier to entry has absolutely cratered. We've moved into the era of PEFT parameter-efficient fine-tuning, specifically things like QLoRa quantized low-rank adaptation.
Okay, break that down for me. No analogies. How does QLoRa actually work without requiring me to mortgage my house for compute?
So, in the old days, if you wanted to fine-tune a model, you had to update every single parameter. If the model had 70 billion parameters, you were calculating gradients for all of them. It was incredibly memory intensive. With LoRa, instead of updating the whole weight matrix, you add a tiny adapter layer. Think of it like a small set of extra weights that sits on the side. You keep the original model frozen. You don't touch its brain, and you only train this tiny sliver of new parameters. We're talking less than 1% of the total model size.
So you're not rewriting the book, you're just adding some very detailed sticky notes in the margins.
And QLoRa takes it a step further by quantizing the base model down to 4-bit, which means you can run the whole training process on consumer-grade hardware or very cheap cloud GPUs. You can fine-tune a Fortune-B parameter model on a single high-end consumer card now. That was unthinkable 3 years ago. Back then, you needed a cluster of A100s just to load the model, let alone train it. Now, a developer can do it on their workstation over a long lunch break.
But wait, if you're only training 1% of the parameters, aren't you losing out on the depth of the learning? How can 1% change the behavior of the other 99%?
It's because of something called the intrinsic dimension of the task. Most tasks don't actually require you to change every neuron in the brain. If you want to teach a model to speak like a pirate, you don't need to change its understanding of physics or how to bake a cake. You just need to shift the linguistic style layer. LoRa captures the essential delta, or change needed for that specific task. It turns out that for most specialized applications, that 1% is more than enough to capture the necessary patterns.
That's wild. But the compute is only one part. What about the data? Daniel mentioned that data curation is 60 to 80% of the project. If I'm a company, where am I getting this gold standard data?
That is the million-dollar question. This is where most projects fail. You need what we call high-signal data. If you feed a model 5,000 examples of mediocre customer service chats, you're going to get a model that is professionally mediocre. In 2026, we're seeing a shift towards synthetic data pipelines. Companies use a teacher model, like a massive frontier model, to generate high-quality examples, which are then vetted by human experts, and that becomes the training set for the smaller student model.
Wait, let's pause there. Using AI to train AI? Doesn't that lead to model collapse or some kind of weird digital inbreeding where the errors just get amplified?
It can if you do it blindly. That's why the human in the loop part is non-negotiable. You don't just let the big model bark out 10,000 examples and hit train. You have a subject matter expert review a statistically significant sample. You use reward models to score the synthetic data. You're basically using the big model to do the heavy lifting of drafting and the humans to do the heavy lifting of truth checking. It's much faster than having a human write 5,000 examples from scratch.
So the big model is the professor writing the curriculum for the small model's intensive boot camp.
Precisely, and you don't need millions of examples. For a style or tone shift, you might only need 500 to 1,000 really good pairs. If you're doing something complex like medical diagnosis or legal reasoning, you might want 5,000 to 10,000. But the quality matters infinitely more than the quantity. If there's even 5% slop in your training data, meaning inconsistent formatting, typos, or factual errors, the model will pick up on those patterns. It's a very sensitive process.
Can you walk me through what slop looks like in a dataset? Is it just spelling errors, or is it more subtle?
It's usually structural. Let's say you're training a model to output JSON. If 2% of your training examples have a trailing comma where they shouldn't, the model will learn that trailing commas are part of the style. It will hallucinate broken code 2% of the time in production. Or, even worse, if your training data for a customer service bot includes examples where the agent was slightly impatient or used and the model will perfectly replicate that impatience. It doesn't know what good is, it only knows what likely is based on the data you gave it.
So, if I give it a bunch of transcripts from my actual support team, and my support team is tired and grumpy on Monday mornings, I'm basically training a Monday morning support bot?
That's why synthetic data is actually often better than real-world data. Real-world data is messy. Synthetic data, when generated by a high-reasoning model and filtered correctly, is clean. It represents the platonic ideal of the task. You take your real-world messy data, give it to GPT-5 or Claude 4, and say clean this up, make it professional, and ensure it follows these 3 rules. Then you use that cleaned version to train your smaller, cheaper model.
What about catastrophic forgetting? I always love that term. It sounds like a sci-fi movie where everyone forgets how to use a spoon. How do we stop a model from becoming a master of SQL but forgetting how to say hello?
It's a real risk. If you overtrain a model on a niche task, the weight shifts so far that the general knowledge evaporates. You end up with a model that can write perfect Python code, but if you ask it, "How are you today?" it tries to answer in a list of integers. The way we handle this in 2026 is through replay buffers, or multitask fine-tuning. Basically, while you're teaching it SQL, you also intersperse a small amount of general conversation data in the training set. It reminds the model, hey, you're still a helpful assistant, don't forget your manners.
Don't forget your manners. You're a SQL bot now. I like it. So, time frame? If I start today with a clean dataset, when is my fine-tuned model ready for production?
For a simple style or formatting task, you could have a prototype in 48 hours. The actual training run might only take a few hours on a decent GPU cluster like what Modal provides. The enterprise-grade stuff. The SQL or specialized medical models usually takes 2 to 6 weeks. Most of that time is spent in the evaluation phase.
Evaluation. That sounds like the boring part that everyone wants to skip.
It's the most important part. You have to run it against holdout datasets that the model hasn't seen to make sure it's actually performing better than the base model and hasn't developed any weird new hallucinations. You use LLM as a judge, where a second, independent model grades the outputs of your fine-tuned model against a rubric. If you skip this, you're flying blind. You might think your model is great because it got 3 questions right, but it might fail on the 4th in a way that's dangerous for your business.
That makes sense. You don't want to release a medical bot that suddenly thinks every symptom is a sign of database corruption because it's been hanging out with the SQL data too much. But here's the big question Daniel posed at the end. Is this all just a bridge? Are we going to reach a point where fine-tuning is irrelevant because the models are so good at in-context learning that the idea of training feels like using a rotary phone?
This is the great debate of 2026. On one hand, you have the context is king camp. They say that once we have 100 million token windows and perfect retrieval, you'll just attach your company's entire history to every prompt. Why bother with the complexity of fine-tuning when you can just provide a massive reference library? But I think there are three reasons fine-tuning stays relevant: latency, cost, and privacy.
Latency is the big one for me. If I'm talking to a voice assistant, I can't wait 3 seconds for it to read. A million tokens of context before it answers my question. It needs to feel snappy, like a human conversation.
Every token you put in a prompt has a computational cost in the pre-fill stage of the LLM. Even with the incredible hardware we have now, a massive prompt takes longer to process than a short one. A fine-tuned model has a short prompt because the knowledge is already in the weights. It doesn't have to read the brand guide, it exists the brand guide. It's snappy. It feels like a real conversation.
And the cost. If you're a startup, you can't be spending 5 cents per query just to remind the bot what your brand colors are. If you're doing 100,000 queries a day, that adds up to a mortgage payment pretty quickly.
Precisely. In-context learning is like renting a room by the hour. Fine-tuning is like buying the house. If you're only staying for a night, rent. If you're living there, buy. And then there's the edge argument. We're seeing more and more models running locally on phones and laptops for privacy reasons. Those devices have limited RAM. You can't fit a million token context window into the memory of a smartphone, at least not yet. But you can fit a fine-tuned 3B parameter model that is a genius at one specific thing.
So fine-tuning becomes the compression of expertise. Instead of carrying around a library, you just become a person who has read the library. It's portable.
I think that's the future. Fine-tuning isn't going away, it's just narrowing its focus. We don't use it to teach facts anymore. RAG is better for that because facts change every day. If your company's pricing changes, you don't want to have to retrain your model. You just update the RAG database. We use fine-tuning to teach skills and behaviors. It's the difference between a model that knows about the law and a model that acts like a lawyer.
Let's talk about that acting part. Does fine-tuning help with multimodal models too? Daniel mentioned multimodal systems in his prompt. If I'm training a model to look at X-rays, is it the same process?
It's similar but even more impactful. General multimodal models are great at seeing a dog or a car, but they aren't naturally good at seeing a hairline fracture in a distal radius. You fine-tune the vision encoder or the projection layer that connects the vision part to the language part. You're essentially teaching the model's eyes what to focus on. Without fine-tuning, the model might get distracted by the digital timestamp on the X-ray. After fine-tuning, it knows that the timestamp is noise and the bone density is the signal.
How does that work with video? If I'm a security company and I want an AI to monitor feeds for suspicious behavior, is that a fine-tuning job?
Very much so. Suspicious behavior is incredibly subjective and context dependent. A general model might see a person running through a mall and flag it as an emergency. But if the model is fine-tuned on data from a specific mall where there's a popular fun run every Saturday morning, it learns to ignore that specific pattern during those specific hours. You're teaching it the baseline for a specific environment. You can't really explain the nuance of 10,000 hours of security footage in a text prompt. You have to show it.
That brings up a fun fact I read recently. Did you know that some of the early multimodal models were actually fine-tuned on video game footage? Like, they used Minecraft and GTA Vive to teach models about spatial awareness and physics because the data was so perfectly labeled.
It's true. It's called embodied AI. By fine-tuning on simulated environments, the models learn how objects interact. Like, if you drop a glass, it breaks. A text-only model knows that because it read it, but a multimodal model fine-tuned on video actually understands the trajectory and the impact. In 2026, we're seeing companies do the same thing for industrial robotics. They fine-tune a general vision language model on their specific factory floor, so the robot knows exactly what a faulty widget looks like on their assembly line.
I wonder if we'll get to a point where the fine-tuning happens automatically. Like, the model watches me work for a week and then says, "Hey, I've updated my weights to match your specific workflow. You don't need to prompt me anymore."
That's effectively what continual learning is aiming for. The problem right now is stability. You don't want your model changing its personality every time you have a bad day and get grumpy with it. Imagine a customer support bot that becomes rude because it's been learning from angry customers all morning. We need better guardrails for that kind of real-time weight adjustment. But personalized fine-tuning is definitely on the horizon for 2027 and beyond.
But back to the present. If I'm a small business owner listening to this and I don't have a team of data scientists, is fine-tuning even an option for me? Or am I stuck with the off-the-shelf personality of the big models?
In 2026, the no-code fine-tuning platforms are actually getting quite good. You can basically upload a CSV of your best conversations and hit a button. The platform handles the QLoRa, the quantization, and the hosting. The real challenge for the small business owner isn't the tech, it's the data. They have to be disciplined enough to save their best interactions. If you have a folder of 200 perfect emails you've sent to clients, you have a training set. If you don't, you're starting from zero.
That's a great takeaway. Start hoarding your gold standard work now, because that's the fuel for your future AI. It's like a digital retirement fund.
Your data is the only thing that differentiates your AI from everyone else's. If everyone is using the same base model from Google or OpenAI, the only way you win is by having the best fine-tuning data.
Well, until then, I'll just keep my sloth-like personality baked into my own neural weights. No fine-tuning required. I've spent years optimizing my low-effort output.
I think your weights are pretty much locked in, Korn. You've reached a state of convergence that most researchers can only dream of.
Hey, I'm optimized for energy efficiency, Herman. It's a feature, not a bug. But seriously, this has been a great deep dive. It's easy to get caught up in the scaling laws and think that just making models bigger solves everything, but Daniel's prompt reminds us that the way we use that intelligence is just as important as the intelligence itself. If a model is too big to be useful, it's just a very expensive paperweight.
It's the last mile problem of AI. You can have the most powerful model in the world, but if it doesn't fit your specific formatting, or it's too slow for your users, or it costs too much to run, it's useless. Fine-tuning is the bridge between general AI and useful AI. It's the difference between a raw block of marble and a finished statue. The marble has the potential to be anything, but the carving is what makes it a masterpiece.
Useful AI. That's a good place to end it. It's about turning that potential into something that actually solves a problem for a human being. Big thanks to Daniel for the prompt. Always keeps us on our toes and forces us to look past the hype of the infinite context headlines. And thanks to Hilbert Flumingtop, our producer, for keeping the gears turning behind the scenes and making sure our own weights stay balanced.
And a huge thank you to Modal for the GPU credits. Without them, we'd be trying to run these scripts on a literal donkey-powered calculator which, well, I have some family members who might take offense to that. Training these models is a compute-heavy sport, and having the right infrastructure makes all the difference.
We'll leave the donkey-based computing for another episode. I'm sure there's a niche task fine-tuning for that, too. This has been My Weird Prompts. If you're finding all this AI talk useful, do us a favor and leave a review on Apple Podcasts or Spotify. It actually makes a huge difference in helping other nerds find the show and keeps us high in the rankings.
You can find all our past episodes, the full transcripts, and the RSS feed at myweirdprompts.com. We also have links there to some of the PEFT libraries we discussed if you want to try fine-tuning your own models at home.
Stay curious, keep prompting, and we'll talk to you next time. Don't let your context window get too cluttered.
See ya.
This episode was produced using Google Gemini 3 Flash, text-to-speech by Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My weird prompts, that's the close from sloth